Hello and welcome to another presentation, this one on integration by substitution, a tricky topic for the students to meet for the first time. Now, it's worth pointing out to them straight away when you're teaching integration by substitution why we've been writing that dx on the end of the integral. I mean, that dx actually has some kind of meaning. Let's take a fairly sort of common place to start for integration by substitution. If we had 4x minus 3 to the 3 over 2 with respect to x. That dx is telling you what variable to integrate with respect to. It's extremely important, and as a result of that we certainly use that dx when we actually integrate by substitution. Now, one of the things I always say to my students when integrating by substitution, I say, firstly pick a sensible substitution. Now here it's pretty obvious that it would be nice if we had a u to the power of 3 over 2. So if we let u equal 4x minus 3, then the second thing I always say to students is they must differentiate. If they're not differentiating in integration by substitution, they're doing something wrong. Naturally, we've got to differentiate. The reason we have to differentiate is so we can decide how we can swap our variable which we're integrating with respect to. Now clearly this is going to be 4, and therefore a quarter du, and this is the way I like to do it, a quarter du is just dx. Now what that's actually telling me is I can swap dx with a quarter du. And naturally, obviously, I can swap u with 4x minus 3 because I have defined u to be 4x minus 3. But that whole differentiation is so you can swap the variable in the substitution. Why does it behave like this? Well, they've normally got the hang at this point in A level. They've normally got the hang of treating dy by dx, du by dx as if it were a fraction. There's many situations actually where we do that. For example, 1 over dy by dx is dx by dy, or indeed chain rule. Chain rule is the obvious one, and in many ways integration by substitution is reverse of chain rule, but for substitution. Anyway, once we've got this, we may now integrate u to the power of 3 over 2. Now I'm going to have to swap dx with a quarter du, but that's no problem at all. And now I can integrate it. U to the power of 3 over 2 integrated with respect to u. Well, I need to increase the power by 1. Divide by the new power, but dividing by 5 over 2 is the same as timesing by 2/5. And I've got to times that by 1/4. And I'm going to have to put a plus c in there. Now, naturally that goes down to u to the 5 over 2 over 10. But u, remember, is 4x minus 3, and that's what I was really supposed to be integrating. So I get 4x minus 3 to the 5 over 2 over 10. Plus a constant c. And integration by substitution has been performed. Let's look at another one so we can get a bit more familiar with integration by substitution. Okay, this one is one of my favourite integrals because I can do it in so many different ways. You will see me in the by parts video integrate it by parts, and you will see me in the other video on integration tricks integrate it using a double angle formulae. But let's have a look how we can integrate it by substitution. Well, the natural choice for the substitution here, and it doesn't really matter if I pick cos x, but if I pick u as sin x, then when I differentiate it, I get cos x, and then if I move the dx across, I can see that du is tradable for cos x dx. That's going to tidy up this integral massively, because suddenly I'm integrating u du. The u is from the sin x, and the cos x dx apparently is the same as du, and so straight away the answer pops out, u squared over 2 plus c, but u of course is sin x, so I get sin squared x over 2 plus c. What a lovely one to do by substitution, and it's also lovely to do in several other ways as well. It's a lovely one to show the students. Okay, I'd like to finish off with a classic, if you like, and it's a classic because it is not obvious that the substitution is going to work. But I'm going to pick for this substitution, let x equal tan theta. Now this is just because I already know the answer to this. For something of the form 1 over 1 plus x squared, also something of the form 1 over the square root of 1 minus x squared, or similar ones to those, a trig substitution is often appropriate. Now, in C4, they always get told the trig substitution in these kind of questions, at least on the exam board I teach. There may be exam boards out there where they expect them to learn which ones are appropriate for trig substitutions. If you already know what the derivatives of things like arc sine, arc cos and arc tan are, then that obviously massively helps you perform these integrals by substitution, and that's the reason why this one's going to work. But let's see how it works out. Always start by differentiating. Tan differentiates to sec squared theta, and so we can see that dx is tradable for sec squared theta d theta. And so what do we have? Well, we have 1 over 1 plus tan squared multiplied by sec squared theta d theta. Might look horrible for a second, but if you remember that 1 plus tan squared is in fact equivalent to sec squared, we actually end up with sec squared theta over sec squared theta with respect to theta. That means that we'll be integrating 1 d theta, which means the answer is just theta plus c, but I want it in terms of x, and so it is in fact going to be arctan x plus c. Like I say, if you want to know how to recognize when a trig substitution might be appropriate, I strongly advise you to learn the derivatives of arc sine, arc cos and arctan, and those will be the ones which work nicely for an integration by substitution. And that's all I really have time for the substitution integration today. I hope that's reminded you of how it works. The one thing you might want to bear in mind though is if there are limits, it's normally easier to change the variable on your limits, to change the limits in other words, rather than to change it back at the end. So yeah, that's something to look out for. Thank you for listening, and I hope you found this useful.